All right, everyone. Good morning. Let's get started here. As usual, if you're attending online, make sure you turn on your camera. So today, let me just pin mine here. All right. Okay, so today, my goal is that we finish the variable rate, the imagery-based variable rate exercise. And then just telling everyone, I know that if you go on the website and if you go on schedule, on the agenda and the schedule for the class, I have a few more dates there, past next Monday, but really next Monday is going to be our last day of class. That I really want to have most of that open in case anyone has issues with the final project. If you have questions, if you got stuck, we're going to do that for during next Monday's class. And I'm hoping that today we can finish the variable rate action exercise in this to be our last actual content related class of the semester. All right, so let's get to it. So I just launched the last project that we created last class called 10 sensor VRN. Right now, I don't have anything in my environment, so this is where we stopped, but I'm just going to go all the way to the top and run everything that we did until now, just so, I can have the variables in my environment, and also we can have a quick refresher on what we're doing. All right, so I'm going to go ahead and load my packages. After that, the first thing we're doing here is bring the imagery that was collected in corn at V12, and that was the timing where we were applying nitrogen. So if you will go ahead and bring that in, we're using read stars because it is a .tif, it is a raster file. So that's why we use stars, because we're working with raster in this case. I also bring a vector, and then I use readsf for that, and I'm calling that plots. So plots basically have the plots that, even though this is a known farm study, it was still a study, right? So we do have plots where some of those plots did receive variable rate nitrogen, and we're going to look into that later. And then, so with those two pieces of information, we're just doing some EDA, as I think we should always be doing that. So here, just taking so remember, NDRE is the normalized difference red edge. It's an index that uses near infrared and red edge band instead of the red band. And we talked a lot about this, and I just want to reemphasize that again. The red band saturates, so it does not differentiate good from really good crop if that crop is healthy, has lots of biomass, and has lots of chlorophyll. And NDRE is one of the options that recover that sensitivity by replacing the red band with the red edge band. This can also be achieved if you replace the red band with the green band, in which case we call this green NDVI. Today, or for this exercise, we're using NDRE. So I just wanted to take a look at the distribution of NDRE. And when I say distribution in this case is using geom density. So it's not geospatial distribution, it's just distribution of the actual values. So here we see that the majority of them are probably around 0.28 NDRE values. And we do have, and it looks pretty normal distribution to me. And that's always good. We also worked on this map here that I wanted to plot the NDRE map that we're seeing. So remember, this is the plot at V12 before receiving variable rate nitrogen application. We see those strips as we talked about last class, and these represent the different treatments that were already applied at planting. And so now we come in season at V12 and take this imagery, we can see the effect of some of those strips going east-west. Also, when we bring in, or when we plot well, I guess we also show that just using map view as well. And I was showing you, maybe you have found this out already, but if the default map view doesn't show you the satellite background, if you want to change that, we did change that through code in one of our exercises. If you don't want to be remembering how specifically to call that to make that happen, you can always just come to this button here and select S3 World Imagery, and that does it for you. So we see it as an irrigated site, which is important. Remember that one of the things we're talking about is when we are using imagery to do variable rate nitrogen specifically, we have to be pretty sure that the main stressor going on in that field is nitrogen related, right? Because if it's not, then applying nitrogen, even a fixed rate, is not going to fix your problems if the most limiting stressor factor is non-nitrogen. In this case here, it is an irrigated study, so we at least know that, you know, the two most common stressors in corn in Nebraska, which is where the study is from, is either nitrogen or water. So since we're controlling for water stress here, being an irrigated field, we, you know, have a large certainty that whatever stress we're seeing is related to nitrogen, especially because we applied different nitrogen treatments pre-plants that we can see on the strips. So then I wanted to create a map of the plots, right? So we see here the plots. So we have three different treatments. We have the grower, the reference, and sense. The only one that's going to be receiving variable rate is the sense treatment. And well, let's go to the next step here. So the next step, here's the thing. So this study, when it happened, when the field did receive variable rate nitrogen, it was using a on-the-go proximal sensor that was mounted to a high clearance applicator, just like we saw on the lecture. In our case here, we are not reproducing that, right? So we are reproducing here the condition that if you have imagery, how could you do, what would be the process to use imagery and create a variable rate map? So we have to take a few more steps if we're using actual imagery and not on the go see and apply. And that's one of those things is if you think of it, the high clearance applicator is sensing the stress and applying a rate that it correlates with that stress as it moves, right? So it doesn't have to have a grid to move because it's just sensing and changing the rate on the go. Because we're using imagery, we do need to create a smaller cells from which we're going to average the NDRE and relate that to a nitrogen rate so that we can feed that into a variable rate applicator in the end. So right now, the plot, especially the variable rate plots, do not have those cells. And that's what we did in the next step here. So the next step, we started with the plots, we made a grid, we changed that to SP, we rotated that, and the angle here, I gave it to you, but the way that I found this was just playing, just trial and error, trying different values, seeing how the grid was tilting, and find the one that it best matched the angle that the actual field boundary was tilted. And then we just did some more wrangling here, and finally we just selected the sense strips, or the sense treatments, which are the ones that we are wanting to apply variable rate to. So if you just run that, it should run all right since we finished in class here. I'm just going to print it, and then I'm just going to plot it. So now when I plotted, notice how we still have all the strips there, but the variable rate nitrogen strips now have been broken down into smaller pieces, which are, if you think of it, each one of those pieces has a potential to receive a different nitrogen rate based on the imagery that we're going to be processing next. Oops. Where was I? All right, so the next step here is the following. So this study here does have a reference strip where it did receive a lot of nitrogen. And we could use that to set the vegetation index, in this case, NDRE value of the reference. If we just went ahead and let's say on this image here, we just found where that strip was and just took the average of all pixels within that strip. We could have done that. That would be using the high nitrogen strip that we talked about in class. However, I want to show you something that is probably going to be more applicable if you do end up using this in a commercial setting, especially. So one issue with the high nitrogen strip is that not all producers want to have a high nitrogen strip. So if they are either opposed to or they just can't legally over apply nitrogen to a strip, as some places have those types of limitations, how can we then have a strip? What would be the way that we can get the value of NDRE that represents a good looking, healthy crop that is not nitrogen deficient, if we do not have a strip that we over apply nitrogen to know that that was not deficient in nitrogen? One solution that has been proposed is what's called a virtual reference. So a virtual reference basically uses the data distribution of that vegetation index for that field and extracts a given quantile from that distribution. In this case, the 95th quantile, and calls that as the reference. It makes sense, and that's what we're going to do next. Even though we did not see this in lecture, but I do want to do this here so we're all familiar with how we would do that. So the first step then is to set our reference, right? Because if you think of it, if you remember from the lecture, we have a reference, and then we use that reference to calculate the sufficiency index, and then we plug that into an algorithm, right? So that's what we're going to do here. First thing is going to be to find what that reference value is by using the virtual reference concept. So if we just come here to this next chunk, we can just use the assignment symbol. We've extracted quantiles before in this class, right? Maybe, I don't know if you recall, but we used a function called quantile. So what we want is the 95th quantile of the NDRE distribution. So the NDRE data is in that object above that we created called pre_NDRE. And it has, we have to say specifically which column inside of that we want to extract the 95th quantile. So if we use the $ to be able to like call the columns, I guess, inside of this object, we use $NDRE, and this is just giving us the NDRE data that we actually were able to, that we plotted on that distribution above on that geom density plot. And then the next argument here is just the quantile itself. So it's just, we just can type 0.95. And then also, because there will be some NAs here, and I just want to make sure that that's not a problem, I want to say NA.rm equals true. So it removes NAs and it still calculates the 95th quantile for us. If you run that and you print it, you should see this value here that our virtual reference is 0.31. Okay, so this would be the value that we are saying this is, nitrogen sufficient crop would look like on an NDRE scale will look like 0.31 units. And just to perhaps put this number in a plot so we can really understand on the distribution what that represents, I left you here some code that we're going to further develop. So, if you just plot this is pretty much the density plot we had above that I showed you. So the density of NDRE, and we're basically looking for the 95th quantile of it, which was like 0.31. So it's probably somewhere around here. But I just want to add that to this plot so we can see that as well. So if you come back to this code that we just ran, you add a plus. We're going to use a geom_v line for vertical line. It has this argument called x-intercept. So that's where you say what number you want a line to be drawn based on the x-axis. In our case, is going to be, we can give it this object name, vrnref, since we already saved that value 0.31 in that object. And I just want to I want to add a comma here and change the color of the line to red. So just say color equals red. If we run this, this is what we get. So we still have that distribution, and here's just the line representing the 95th quantile of this distribution, which we are calling this as our high nitrogen reference. And in this case, it's a virtual reference because we don't actually have, well, I guess in this case, we do have a high nitrogen strip, but I just wanted to show you in case you don't have, you can use the concept of a virtual reference, which is what we just did. Okay.
Dr. Vesper, it's giving me error, no loop for weight coordinates.
On the plot,
Yeah.
did you write a plus?
Yeah. You be going next. Getting the same thing? Oh, we'll check it out.
So just make sure that when you print via nref that you get this back.
Yeah.
Okay. Because yeah, if you get the reference value set up right, that's good. Yeah. Okay, so here's the thing now. If you look at this, let me just show you. Even with yes.
I had a question real quick about the na.rm equals true.
Mhm.
What, like, is there a certain package that can only be used with, or can it be used across the board? Is that like a base package?
You mean the argument ni.rm, na.rm?
That's correct.
So this is an argument, right? So it would be applicable to the functions that have that as an argument. So it's not really related to, it's not like you can take this argument and apply to any function that you may come across. The places I've seen this this argument, especially this way, appearing most commonly are with these functions that we are extracting statistical summaries, right? So minimum, maximum, mean, median, quantile, SD for standard deviation. So those functions all accept this argument here. And maybe there are other functions that, that I'm not saying here that also accept that argument. I think, if you have a function that you're just curious, you can just try to plug it in and see if it works. If that function doesn't accept this argument, it's just going to throw you an error and say that. Another thing that you can also do, so let's say if you're running a function and you're given in a data set that has NAs in it, and you want to maybe like remove those NAs before you feed that into a function, so you don't have whatever could happen when you're given NAs, you can just do like a drop NA. So there's a function called drop NA. So let's say if you have a set called like df, and then you drop NA, and then you feed that into a function like quantile. You can also do that, which is not within the function itself, but it's like outside of that, but it should have the same effect.
Right, and that has that drop NA has to be at the front of the chunk, or can it be at like the end of the chunk? Does it matter?
Well, it should at least be before the function that you're trying to feed data without NAs, right? So if that function quantile, it should come before quantile.
Okay, thank you.
Yeah.
Dr. Like, what is the difference than na.omit? It will also do the same thing.
That's a good question that I don't think I've ever really looked into that. So Arminder is asking that there's a function called na.omit. I think na.omit, is that a function or an argument? Yeah, I don't remember. Let's just try to do a help na.omit and see if that is a function. Yeah, it is a function. So there is this one from stats package. I mean, I'm not going to spend a lot of time here, but if you want to understand that, I would go through this documentation here and see, what it's doing, and perhaps play around with data that has NAs and do NA remove, drop NA omit, and understand, play around on your side and understand that. But that's a good question. Yeah. All right, so let's keep going here. So here's the thing, even though, so we're going to be applying variable rate on these strips here, and each one of those cells within the strip could receive a differentiation rate based on the NDRE data behind it. Nonetheless, this image is coming from a drone, which has a very high spatial resolution. So even though we're breaking this strip into smaller pieces, there are still multiple NDRE pixels within each one of those pieces. So what we have to do basically is to average the NDRE for each one of those pieces and have one NDRE value that then we use that to calculate variable rate. So that's what we're going to be doing next in this chunk here. So I'm calling this, so we're going to extract NDRE from the grid. So the first thing we have to do is I want to basically crop that NDRE map using the shape that we just created here with all the splits or with all the breaks for each one of the variable rate strips. So let's go ahead and do that in this next chunk here. I want to first thing call the pre_NDRE object, which is the one that has all the NDRE values at this point. And then I use a pipe. I'm going to use the function called stcrop and give it the object we just created above called grid_VRN. So grid VRN is this one here, right? That has all the breaks. So that's the grid VRN one. So if we do this, it may take a moment here. And then, I mean, you can go ahead and print it just to check, but it is a stars object, so it doesn't print as nicely as an SF object. And then I want to plot. I want to see what happened when I used the stcrop, right? So I left you most of the code there. We're really only changing a couple things. So I'm starting with the ggplot. I want to add this geom stars to show this grid NDRE. So the data argument here is going to be grid_NDRE because I want to show that stars object that we just cropped. And then I also want to show the grid itself behind it, right? So for that, the grid itself is called this object here, grid_VRN. So on the geom_SF there, you just have to change those 3 dots by grid_VRN so we can show that. And then I'm just changing here the fill to be very discontinuous, changing some of the theme options, and that's all that this ggplot is doing. So if you go ahead and you run it, this is what happens. So I guess actually what I explained earlier is the next step. So right now we're not averaging yet. We're not averaging yet, but we're at least cropping that NDRE map or raster that we had for the whole field. We're just cropping that to the VRN strips because we know those are the only ones, at least in this study, that were receiving variable rate. If you were doing this on a farmer's field and you were applying variable rate to the entire field, then you would not be doing this step here, right? Because you would not have to crop it to only some strips. You would actually be using NDRE for the whole field to do variable rate. All right. So I guess this is the point that I was telling earlier, that if you look closely, we still have multiple pixels within each one of those cells, right? And the spatial resolution of this image is 30 centimeters, so it's about a foot. So we have a lot of data still within each one of those cells. And if you think of it, if we wanted to use the native spatial resolution of this of a foot, that's probably, I mean, that is unrealistic for sure, right? I don't know of any variable rate equipment that can change a rate as fast as every foot, you know, at a given speed. That is just very, very high resolution. We don't need that resolution. And we also, even if we needed, we would most likely not be able to implement that resolution just because the equipment couldn't handle it. And so we're gonna average those pixels within each one of those little cells. Yeah.
I have a question.
Mhm.
So what it means, because you said at the end of the day, we have to average for each pixel, right?
For each one of the cells that we created.
It's
Yeah.
like how, I didn't understand, like how we selected the say, like why we use the
How we selected.
like when you like when we chose the cell size.
Oh, the cell size. Okay. So the cell size that okay, so Peter is asking like, how do we define the cell size that we're using to have to, on the next step, average the NDRE values? So that was done here, right? So the cell size is basically, so a couple things here. This study already had those strips, right? Created before we had to break those strips down into smaller cells. So these strips here were I guess the height of that strip was determined based on the equipment that the producer had, the swath of that equipment, right? So that's how the height of those long strips was determined. And that's something that we're not changing here, right? What we are changing, and this is something that if you're applying variable rate commercially, you would still have to have strips because those would represent the swath of the equipment, right? So this is something you would still have to do. But I didn't show you how to do this grid here, but you already know how to do grids from different different exercises.
The height or the length of the strip?
The height of, in this case here, the height of the strip is the swath.
But it's the length.
The length is what we changed, right? I just wanted to tell here. So the height is the swath. Now the length, if you think of it.
No, like in the field, when you say height, right? Yeah.
So like right here, so if we take one of these long strips, right? The height of that strip is this like on this axis, on the y-axis. This height is the swath.
I can think about it like the width of the strip.
Yeah, you can think of the width of the strip. Yeah,
Okay.
yeah. So the width of the strip here was created in a way to match the swath of the equipment of that grower, right? So this here is something that is like grower specific depending on their equipment. Now the length that we decided to cut that into smaller pieces, which is something that we actually did. Here I chose 6 meters. You know, I think this value here has to come down, also related to like how fast the equipment can change rates in a reliable way, right? I don't remember exactly how we arrived at this number, but I think it was related to that specific sprayer that we were using, and that was a width that we determined was a good width to have a good response of the system. So this is a really interesting point, because if you think of it, so this was a high clearance like liquid fertilizer sprayer, right? If you're using like a dry spreader or different types of applying nitrogen or any input really, your lag time to change from one rate to the other could change depending on that equipment. It could change depending on the hydraulics behind it and how that variable rate is set up, right? So this value here should be higher for different systems. But of course, then there's that trade-off that the bigger you make, so this 6 here would be the length of each one of those cells, right? Of course, we have then a trade-off that the larger we make that 6 is going to give you a larger area for a given split, which means you're averaging more NDRE and you're having less opportunity to vary nitrogen in space. But there is a trade-off there between how much you can manage and how much the equipment can handle as well, right?
Changing rates in all the cells.
Potentially each little cell here could have a different rate. Yeah.
But as VRM also takes time to change.
Yeah, well, for this equipment setup here, that was doable. I now that I'm thinking, I think the way that we determined that number 6 was we actually have an as applied map from that variable rate equipment that was applying on the go, and it had a new point every 6 meters. So we just assumed that was how much the capacity of that equipment. Yeah.
So simply, there is no length of the ore strip in this. The ore strip, there's like 300 go to this. That's the case.
No, so even though, yeah, so we're treating variable rate the entire strip, but we have to, for that to be variable rate, it has to have the capacity of apply different rates in smaller increments, right? Yeah. So the other treatments here did receive a fixed rate across the entire strip. the others that were not VRN, right?
Oh,
For the VRN ones, they're receiving small increments or small increments of land are receiving potentially different nitrogen rates. Yeah, that's what we're doing here.
oh, so where we see there's no those strip is uniform.
Yeah, so let me just show you this other map here again. Yeah, so here we see that the blue strips are the sense strips are the ones that receive variable rate. And the other two are either grower or reference, and those receive the fixed rate, the same rate across.
So if I say the length of the strip is 300, you put over there, we are 50.
You
Length
would,
of the whole strip, strip from west to east.
it would be true for the grower or the reference, not for the sense. The sense strip received variable rate, which we're calculating next.
Oh, no, I am trying to get the intuition of that 300, what is it representing? Now I get like this.
Which
60 meter
which
on the
300?
same, on the, yeah, it's
Here.
300, yeah.
This is just because I want it to be larger than the field, that's all. I mean, if we were. So I don't want to spend a lot of time on this because that's not the main goal, but on your side, change this to 10 and see what happens.
Oh,
Like later,
oh,
after class,
Yeah.
play around yourself and figure that. I think that's a good way of learning as well. But yeah, this is just making a very long cell that I know is going to cut through all the VRN strips. That's all. All right, so let's keep going here. So we stopped here at the point where we cropped that entire NDRE map to only contain the NDRE pixels that were within the variable rate strips, because those are the only ones receiving variable rate nitrogen. But now we still have to average, right? And only have one average NDRE value for each one of those small cells. So that's what we're going to do next here. Okay, so we're starting off with the grid NDRE, which is this object that we just created above here that we're plotting right there. So we're starting off with that. At a pipe, we're going to use a function called st_extract. So here we're going to say that we want to use that NDRE there and extract something. In our case, going to be the mean, but we have to tell it extract from where. Because right now, grid NDRE, like if I were to not show the grid VRN, but just grid NDRE. Grid NDRE is just that NDRE like that, right? So I have to tell it how I want to extract the average, like what cookie cutter I'm going to use to extract the average, which is the grid VRN, right? So grid VRN is the actual little cells there. So we say st_extract, we say grid_VRN to say what is our cookie cutter that we want to extract the average of. And also just make sure you do na.rm equals true. I guess, Ethan, this is an interesting example that st_extract by default extracts the mean. And because it is doing the mean behind the scenes, we can give na.rm here, even though the function that we're calling is not mean, but is doing the mean behind the scenes. So I guess that was an interesting point.
Well, that's what I was asking, because I've noticed that we've used it in several different places, but like every time I've been trying to use it in my project, it's like, no, it cannot be put here. So I was like, where can it be put then? So I wasn't sure if it was like a base function or if I was missing something. So
yeah. No, it's here we can do that because behind the scenes st_extract is using a function, right? And the default function is mean. So that's kind of, it's just like taking that argument and passing it on to the behind the scenes function of mean. Yeah, but I guess just wanted to call that here. So if we do that, if you run that, okay, this may take just a moment here, and I guess I actually should have showed you the next step before running it. But I guess I was trying to make the point that when we run this through st_extract, the result is not an SF object anymore. And we do want that to be, or maybe it is a stars object and I want that to be stars, or maybe it is stars and I want it to be SF. So I guess we're gonna have to wait for that to go through anyways. So mine is still running. I don't know if on your side that is still running as well. Yeah, let's just give it a moment here. And let it go through, let that go through. But the next step here that we're gonna do, yeah, okay, so mine just finished, and if I printed, well, so it is a stars object, yes, so it is still a stars object, but I do want that to be a vector object after this. So to do that, we add a pipe, and if you recall, we're gonna use the function st_s_sf. So that is basically going to transform this stars raster object into a SF vector object right there. So if you go ahead and run that, let's just give it a moment to go through. And then I guess I'm going to tell you what we're going to be doing on the next part of this chunk here as that is running. So I want to make a map that I really want to show now. Is going to be similar to this map above, but instead of having multiple pixels per each one of the little cells, we're actually going to have just one average value for each one of those cells. And I just want to show that here in this next piece of the code. So whenever this goes through, we're starting with a ggplot. We're calling geom_sf to show this object here that we just transformed that into an SF object. So that's why we're using geom_sf. So mine just finished running. I'm gonna move on here just so you can see. If you're still running on your side, that's okay. You'll be able to catch up soon. So just change the data to that grid _ndre_av for average. And if you run that and you print it, this is what you should be seeing now. And notice how now we have just one value for each one of those cells, right? And that's because we want to apply one rate within which one of those cells. So we have to have one NDRE value to do that. Okay, so now we have our reference set up. Our reference value does not change, is fixed for this entire field for this image. We have the cell NDRE value that we're going to use now to calculate sufficiency index. So let's go ahead and do that next here. If you go to the next chunk, we're going to be calculating sufficiency index, just like we did in class. So we're starting off with this object above here. So with this object right there, I'm using ST_as_SF again. I don't remember why I have that there, but since it is there, I'm going to leave there to avoid errors that may happen if we just remove it. So if you come to below this comment here is saying setting reference, I want to create. Let me just print grid NDRE AV so you can see. This is what the data kind of looks like. It has like 759 rows because that's the number of cells that we have the average of NDRE for. And now I need to have a column here. So I have the NDRE column, right? Which is the average for each one of the cells. I need to have a column here that I'm going to call reference and have that fixed value of reference running all the way through this data set. So we're going to use a mutate. Every time we're creating new columns, we use mutate. I want to call this NDRE_ref, say equals to. And if you recall, we calculated the NDRE reference value, and we saved that into an object that we called VRN_ref. If I just print this object by itself, it's that 95th quantile of, oops. It's that 95th quantile that has a value of 0.31. So if we just put that here and run it, and now I just print SI, still the same data of the same number of rows, but now it has a column that's called NDRE ref, and it has the same value running down all of this, right? So we have a column with the field NDRE, we have a column with the reference NDRE. Now let's go ahead, add a pipe at the end here and come after that second comment, and let's use another mutate to calculate the actual sufficiency index. So SI equals to what? how would you calculate, knowing that NDRE and NDRE ref are the number of the columns we have, how would you calculate sufficiency index in this formula? Can somebody help me? Amrinder.
NDRE divide
By reference.
NDRE by reference, right? Pretty straightforward. So we're just gonna start typing here. NDRE divided by NDRE ref. That's pretty much it. That's how we do SI. What you did in class by hand for one cell, if you think of it, we're doing for 759 cells in this case, using that line of code. So if we run that and we print it, we have a new column called SI that now ranges from probably 0 to 1. So the values closer to 1 means that that cell was pretty close to the reference. Values near 0 means that they were very different, very stressed cells in that case. As always, let's just go ahead and plot this so we can see this in actually how this looks like. So I left you most of the code. The only thing you're changing is the data. So data equals SI. That's the object that we just created above. We'll just change that and run this. And this is how it looks like. So now we have SI that ranges from about 0.5 to about 0.95 probably. And we see yeah, we can see here, so the places that are darker in color are the ones that are most stressed and are probably going to receive the highest rates. And the places that are yellow are the ones that were pretty healthy, very similar to the reference and receiving a lower rate. Okay, so if you recall from class, when we did this by hand, now we have the SI. The next step is going to be to plug this into the algorithm. So let's do that next on the next chunk here. So we're going to be using, again, the Hall and Shepherd's algorithm. And I just want some help from some of you. Let me call someone that hasn't helped me yet. So the Hall and Shepherd's variable rate nitrogen formula required a few different inputs, right? What were those inputs? What do we need to establish here to be able to calculate that? Let me ask Emma, do you remember of what we needed here for that algorithm?
Like the previous nitrogen credits?
Yes, so nitrogen credit was one of the things we needed. Thanks, Emma. Someone else, let me ask Miller in Tifton. What else, Miller, do we need here?
Don't you need, like, have to have a yield goal set to know how much to apply to begin with?
So we were not using yield goal. We were just going on with the assumption that you would ask a farmer about, like, what is the rate that you believe is optimal for your field. That's kind of the way that we phrased that. But how do you remember how was that called here in this formula?
Like the sufficiency index, isn't that what it?
So, well, I thought you were saying something else, but are you talking about sufficiency index? That's what we need here?
Yes.
I agree. Sufficiency index is something we need. We just calculated above. Let me go to Sarah. Sarah, what else do we need here to calculate variable rate with this algorithm?
I think there was something about economy rate of nitrogen that we should apply.
Yes, that's exactly right. It was the last piece we were missing. So EONR, right? So the economic optimal nitrogen rate, which is that rate that the producer will probably tell you, this is the rate I've been using. That's what you would plug into there. This could also be derived by yield goal, but we're not going to get into that conversation. But yeah, it could also be done that way, as Miller was referring to. All right, thanks everyone for the help. So we need these three pieces of information, right?
What about the change in SI?
So the delta SI is going to be fixed, right? We also need that. That's a good point. We also need that. And that value is, so I mean, we can write here delta SI. That value is going to be fixed for, the way that I'm showing it here, it would be fixed for every field, right? So it's not something that's going to change from field to field. And credit and EONR will change from field to field. SI will change from cell to cell, right? So SI is the one that's very specific to the cell. All right, so let's get through that here. Let's calculate our actual variable rate nitrogen for those cells. So I'm starting off with the object called SI. We're saving that to the result of all that to an object called VRN. So if we're starting with the object SI, this is what we have. So we have NDRE, we have the reference, and we have SI. Really, all we need from here at this point is just that SI. So SI, check, we have that. However, we still have to define nitrogen credit, the optimal nitrogen rate, and that's what we're going to determine in this next step here. So if you come on this mutate, the first thing I want to tell you is so on the algorithm is called nopt, right? So that nopt was that EONR, but I want to call the same as the algorithm was calling. So nopt is going to be equals to, for this field here, it was 229 pounds of N per acre. So we have nopt, which is our EONR. The next thing, I just added a comma in head return, so we can, on the same mutate, you can create multiple columns at once. That's what we're going to be doing here. So the nopt is 229. The next one is, so if we applied any pre-plant fertilizer, that would come as one of the credits. The way that's called is N-pre. That's how you would refer to it based on the algorithm and the way they call it. So for the VRN strips, we applied 0 at pre-plant, so that equals to 0 pounds per acre. And finally, N credits, I'm going to call that N cred. This field here is receiving a credit of 20 pounds of N per acre. I think it's because the previous crop was soybeans, and for Nebraska, that's the credit that they give when the previous crop is a legume. So so defining the optimum, removing any credits, and then applying that to the algorithm part. So N-pre is the application of nitrogen pre-plant or at planting, right? Because we're coming here at V12. So the crop is already growing, right? So if you apply any nitrogen before your side dress application that we're doing now, this is where you would specify that. Say that again?
Do we need N3 now?
If you did apply, you would need, right? But I mean, in this case, it's 0. So if you have it or don't have it, doesn't matter. But I just wanted to have it there just to show, how the workflow would be. N-pre is the nitrogen that was applied, let's say, pre-plant or at planting. Right, so normally growers would apply some nitrogen at near planting and then some nitrogen in season. If any nitrogen was applied before the in-season application, which is the one that we are mimicking here, then that's where you would give that credit. Okay, so I'm just gonna, you don't have to do this I'm doing right now, just. Yeah, is the optimum nitrogen for that field. Yeah. I just want to run this just so you can see the columns. So we have NDRE, NDRE ref, SI, and now N optimum, N pre, and N cred are just a single value running all the way down through this data set. So now we pretty much have everything we need to calculate our variable rate nitrogen in pounds per acre. I just left some filled in the blanks for you there, which is basically, we start off with how much we need total, right, which is N opt. So the first 3 dots, you just delete them and you replace by N optimum that we just created above. And then you deduct any credits, right? In this case here, we created the credits N pre, which in this case is 0, so minus N pre, and also minus N cred, that are other credits related to, in this case, previous crop, right? So we define how much we need total, we remove anything that we may have as a credit, and then that gives us a rate. That's, in this case, this part of the algorithm is calculating 209, and then that rate is being modulated by the sensor part of it. I left you the formula there because it can be tricky to type this and make sure everyone has the parentheses right. So I left you there, but it's pretty much what we did in class, where we have the SI changing for each one of the cells. So if you go ahead and run that, and you print it, now we have a column that is variable rate nitrogen in pounds of N per acre, and this is our actual variable rate prescription. That's where the data is. I do want to tell you all that, so class, we only go to 10 today. So class is, I mean, we reached that time. I do want to continue going through this exercise and finish this lecture today because I want to leave Monday just for the final project questions. If you do have to leave at 10, feel free to do so. Before you do, let me just open attendance for today. And then you can take attendance and leave if you have to. If you can and you want to stick around, you're welcome to. We're going to go through this exercise through the end. Attendance 28. And if you have to leave, so I just opened GitHub. If you have to leave, you can claim your attendance now. If you don't have to leave, you can wait until we finish in the next 10 minutes or so. But anyways, regardless if you decide, I mean, if you have to leave now, you're welcome to, but you will still have to watch the recording afterwards so you get to the end of this exercise, which we're almost there. All right, I'm just gonna keep going here for another 10 minutes or so, and so we can finish this. So we just calculated now the variable rate nitrogen in pounds of N per acre, right? That's what we needed. That's what we were doing and going after. So on this next chunk here that I left you, I just wanted to explore again using a density plot, how this rate was changing for those strips. If you just go ahead and run that, here's how the rate was changing. So the average rate that was being applied side dress was probably around 155, 150, somewhere there. The minimum was just above 850. Sorry, the minimum was just above 50 pounds of N per acre. The maximum was, I don't know, 260 or so. So we see now that if you're applying a fixed rate, you're really applying to the mean of the field, right? So let's say if we were applying a fixed rate of 150 side dress, we would be treating the average of the field pretty well. But the tails, some tails, if we were applied a fixed rate, some tails would be under fertilized, other tails would be over fertilized. So variable rate nutrient, in this case, nitrogen management, allows us to modulate the rate and accommodate better the tails of this distribution as compared to just applying a fixed rate to the entire strip. Okay, and as always, I like maps, I like plots, I like to see the data and not just have as tables. Let's create a map here in this next chunk. Basically, I just want to show you the variable rate changing for those different cells. So I left you most of the code. We just have to change here the fill. So the fill, I want to change the fill of those cells according to the VRN pounds per acre column. So that's what we would change here on this 3 dots on fill, change that to VRN underscore pounds per acre. And I'm saving that to this object called VRN map. So this is our actual variable rate prescription map for those strips, right? So we see how the rates are changing, and they do change a lot, right? Especially some of these strips here have a very wide range of those rates going across the strip. So I think that's pretty exciting. Okay, so next thing I want to do here is I want us to look at a couple of plots side by side so we can understand how SI and NDRE, how NDRE, SI, and rate are all related. So come to the next chunk here, we're loading the package Patchwork. If you remember, Patchwork allows us to combine multiple ggplot objects. I want to show, the first one I want to bring is the NDRE underscore map that we created above. So if you print that, this is how it looks like. So it is the map with NDRE. And I want to have right below it the VRN map. So to bring a map below it, we use the / symbol. And then we're going to call the VRN map that we just created above, that's called VRN underscore map. So if you run that, this is what you should be seeing. Oh, I don't know what mine is. Okay. This is what you should be seeing. So the top map is NDRE, as you can see on the legend. The bottom map is variable rate nitrogen, pounds of nitrogen per acre, as you can see on the legend as well. So let me ask someone else that hasn't helped yet. How like, can you point to maybe one part of this field and tell me how NDRE is related to variable rate? Like the NDRE is low and or high, and that makes variable rate to goes up or high, and you can see that on a specific part of this map. Let me ask David. What do you think, David?
On the right corner where the NDRE is high, you can see the yellow. You go down to the second one and the price is a lot lower, the application on that right side. So
Right, perfect. So I don't know if people online were able to hear, but David said on the right side here, we see that NDRE is higher. And when we look at the variable rate application map, that's where it's receiving the least nitrogen. So I agree with that. And we can also see the opposite in other places, right? So where we have NDRE being very low, so we see here on the left side, some strips having very low NDRE, that's also where the highest nitrogen rate is, right? So that's how the algorithm was using NDRE, relating that to the reference, and then creating a rate based on that. Okay, so lastly, so if you are doing this for a producer and they have variable rate nitrogen capabilities or equipment to actually apply this, of course, we have to export this so they can use. We just went through the exercise of creating that prescription. Now let's export this so we can share that with our grower. So we're starting with VRN. Let's just add a pipe. So right now, VRN, this object VRN has NDRE, NDRE ref, efficiency index, and optimum, pre, cred, and VRN. Maybe a grower would like to see all those, but just from a application standpoint, they really only need two things out of this. One is the actual variable rate, right? That's what they need to change the rate as they move through the field. And the next one, because this is an SF object, the geometry, right? So I want to do a deployer select, only get the variable rate and the geometry to make it simpler. And then export this to file or save this to file. We're going to use the function write_SF because it is an SF object. We open and close quotation marks, get outside of the code folder, get inside of the output folder in this case. I do want to export this as a shapefile because a producer will most likely use a shapefile on their equipment instead of a GeoJSON. So I want to come here on my files. I want to go on output and create a VRN folder there. As you remember, shapefiles create at least 4 files to go along with that. So if you have that mixed with other files that are not related to that shapefile, things can get a little bit messy to track. So I just want to have a folder that we're going to save all the shapefiles and associated files inside. So if you did create that VRN folder inside of your output, you can just navigate to that here on the path that we're specifying. And I just want to call this object or this file here vrn.shb. Also remember that to always change this argument called delete_dsn to be equals to true. This will for sure save you a headache in case you rerun this script again, especially this part of the code here when we're exporting. So if you run that and then you browse here on your VRN folder, you should have now four files where one of them is the actual SHB that we asked to export, and the other 3 ones are just associated files that go with that shapefile. And again, if you ever worked with shapefiles and share shapefiles with people, you will have to send all these files. If you only send the SHB, the other person will not be able to use it. Okay, so I have one last chunk here, or maybe a couple more that I think are pretty cool. So the reason why I decided to show you this specific site is because this was a site that actually those trips truly receive variable rate nitrogen. And we can really see the aftermath of that. So the image I sent you was at V12. So that was the image right before that field received variable rate nitrogen application. So the next day or two after that image, the field did receive variable rate application on those strips. And then we have an image from when the crop was at tasseling. So maybe like a few weeks or a couple weeks after the first image that we have. So I'm just, I left you the code here to bring in that image. So it's called ndre_post VT. I left you that first part of the code. You can go ahead and run that at least. And then we're going to plot that, right? So I'm using geom stars just like before, and you just have to change those 3 dots. So if you just delete the 3 dots and you just bring in this object called post_ndre, which is the one after application. If you run that and you print it, this is how it looks like. So this is again, so NDRE values are higher overall. That's expected because now the crop is taller, has more biomass, has more nitrogen in that biomass. It is more, it has moved ahead in its development and growth. So overall, we would expect to have higher NDRE values. And this is how it looks like. And even though this by itself is very interesting, but I do want to show you, I do want to combine the imagery that we had before application and this one that was after application side by side, just so we can compare them in the same plot. So to do that, we're gonna again use, so we're gonna call the pre-variable rate NDRE map that we already created above, and we save that on an object called pre_NDRE_map. So if we just print that, this is the one before application. I want to bring right below it the one that we just created above. So to do that, we're going to use the /. Remember, this is coming from the patchwork package that allows us to combine multiple plots into one output. And then just call the one that we created above, just above, which is called post_NDRE_map. So if we run that, this is for comparison, right? So again, the one on top is the one before VRN. The one on the bottom is the one after VRN. And remember that VRN only happened on the VRN strips. It did not happen on all the strips, right? So I guess a question that I would have for someone here is, what do you see different from before and after nitrogen application? Let me look for someone else to help me here. So let's see, Trip, are you there?
Yes.
Awesome. Trip, what are you seeing here?
It looks more like consistent, like there's less variation between the field.
Okay. Anything else?
There's not really those strips anymore.
Right. That's a great point. So here's something very interesting to realize here. We don't see the stripping going east-west anymore on the afterwards. That's basically because those strips were actually representing the variable rate treatments that at that point were undergoing some stress. And now we basically we were able to mitigate that stress by applying variable rate nitrogen. However, very interestingly, we still see some spots that have low NDRE. And let me tell you what's going on here. So these are just parts of the field that are sandier. So even though we removed the stress that was initially caused by nitrogen stress in the beginning, however, the underlying major problem that this field has is more related to soil variability, to soil properties. In this case, even if you apply nitrogen, more nitrogen or variable nitrogen to the different parts of the field, it was still not able to recover on those specific parts where it has like a sandier soil across that field. So it's just a limitation of the field itself. But I thought it was so interesting to see that initial stress of nitrogen that we could see on the east-west strips, we addressed that. Even though there's still some stress that perhaps is more difficult to address, even with a fixed rate, because it's something, the major driving factor is more related to soils than it is to management. So I just wanted to point that out. Thanks, Trip, for helping out here. So I think that was all that we have for today or for this exercise. You know, just a very quick summary. We brought in UAV imagery. We extracted the reference of that imagery. We used that reference to create variable rate nitrogen grid, and then averaged for each one of the cells, calculated sufficiency index, calculated variable rate nitrogen, exported this as a shapefile, and then lastly, just validated that with a post-application imagery to see the effect of that variable rate. So this is all I had for today. I know we're already past the time. Thanks if you could stick around. And if you couldn't, I hope you can catch up later with the video. If you have any questions from today, I'm going to be here for the next 5 minutes. And if not, I'll see you on Monday, which will be our last encounter, I guess, of the semester. And we're going to be saving that time to talk about the mini project or the final project if you have any questions or issues with code related to that. All right, if you don't have any questions, you're free to go. And I'll stick around for a little bit longer, but if not, if nothing else, I'll see you on Monday.